Welcome to Chapter 10. Congratulations, you have made it to the last t-test that we will talk about. So far you have learned the one sample t-test, the independent t-test, and now you're going to learn about the paired samples t-test. So let's check and see what type of design requires us to use a paired t-test. So if we're talking about research designs, a paired t-test is when we're using a within subjects design. So remember with the independent t-test, that was a between subjects design. With a paired t-test, that's actually considered a within subjects design, which is where we have the same participants observed in two or more conditions. So that's just in the design. So the same people in two or more conditions or two points of time, basically. So if you'll notice, we have in this example, student success in three different conditions of mentoring. So basically, Jeff, Mary, Sydney, Kathy, and Buddy were in each of these three conditions. So because it's the same participants, it's considered a within subjects design. And within subjects can be two conditions, can be three conditions, it can be 5, 12 conditions, however many conditions. But very specifically, when we're using a paired samples t-test, it's when we have the same participants in two conditions or 2 points of time for the same people. So we no longer have an independence of the people. Um, so there's no longer different people in each of the conditions. It's the same people in both conditions. So remember t-tests, that T is kind of stands for two. So in a one sample t-test, you still have two means. You have the sample mean and the population mean. In the independent measures t-test, you still have you have two means, mean one and mean two. In a paired samples t-test, that T is for two conditions. So it's all related to two, basically. So the paired samples t-test is known by a lot of different terms. I call it the paired samples t-test because that's a lot what most of the software for statistics uses is the term paired samples t-test. But you may also hear terms like the within subjects t-test, a related samples t-test, a dependent samples t-test, a correlated samples t-test, or even a repeated measures t-test. So lots of different terms mean the same thing, but I'm going to specifically refer to it as the paired t-test is what I will do. So the paired samples t-test, again, there's two scores for each person or for each individual. So um, subjects, the same people are used in each of the condition, and this helps us to kind of um, lower the risk of maybe the differences in the people's individual differences, their characteristics or traits that differ between groups becoming a big impact. Because if I'm using the same person in each condition, their characteristics or traits are going to be the same. It's the condition that's going to change things. So as you can see, we have students Jim, Tracy, Corey, Chris, and Cole. They're in a before student mentoring and an after 6 months of student mentoring. So just those two conditions, but same students in each of those. So that's when we would use that paired t-test. So there is one type of design that um, uses the paired samples, but it's not necessarily a a traditional paired samples t-test. It is in the design, it's called a matched subjects design. So basically, there are different participants in each of the two conditions or for a paired t-test, but the participants are matched on some characteristics or traits. So you would still calculate it using the paired t-test, but it's all actually called a matched samples design. Um, so you have two different participants in each, but they're matched on characteristic or traits to where basically it's like having a pinch hitter, like in baseball, if, like your legs hurt, um, you're gonna hit the ball, but you're gonna have a runner for you. That's basically what's happening in this. And in reality, in social behavioral sciences, this is the type of test that we use when we're using like identical twin studies. It's a matched subjects design. So it's all in the design. So if I had used a paired t-test, I have a sample of 10 participants, there's 10 people that those same 10 participants are in condition 1 and condition 2. If I'm using a matched samples t-test, I would have 10 participants in sample 1 and 10 different participants in sample 2, but their traits are matched to the extent where they're basically a stand-in for the original person. It's all about the design. The calculations would be the same as the paired t-test. So, why would we choose a paired samples t-test over like an independent t-test? Well, for one, um, if if it's conducive, we can look at running a t-test and having fewer participants. So, if you remember, we to meet normality, we either need to make sure that we're sampling from a normal population or use a sample size of 30 or more. To get that normality for an independent t-test, that means 30 in each condition. So if you have two conditions, you need to have at least 60 participants for to meet normality. Well, with a paired samples t-test, because each of the participants are in all the same participants are in sample 1, sample 2, you'd need fewer participants. So you would only need 30 participants rather than 60. So that is a much more practical reason for a paired samples t-test. In addition, we can look at changes over time, which is very effective, especially if we're looking at things like therapeutic treatments, like for depression. We want to see how depression changes over time rather than between people. And so it's a very effective type of study for social behavioral research. And again, like I had kind of mentioned before, it controls for the individual differences. So if we have the same people used in each condition, it reduces the error that's found just due to traits or characteristic differences because the same person is in the first sample that is in the second sample. So you're only measuring the difference in the treatment effect rather than possibly the error contributed to the difference in characteristics or traits between people. So it lowers the error, the standard error, or just the error in general, and it increases the power of the test, is what it does. So, a paired samples t-test is extremely useful in social behavioral research. So, with the paired t-test, just like with an independent t and a one sample t-test, we do have assumptions to make sure that our results are valid. The first one, just like the others, is normality. So, two ways that we can assure normality is either sample a size of 30 or better, or make sure that we're removing uh, the sample from a normal population distribution. So those are two ways. And then for this, instead of independence between groups, we have independence within groups. So basically, that sample of 5 people, they're in two different conditions. You just need to make sure that the scores within the group are independent of one another. So no individual score is impacted by other scores within that group. So it's independent within the groups. So you're not participating as a team, basically. You're doing it as an individual. So here's I'm going to present the things that will change for the paired t-test besides just why we're doing it and when to choose a paired t-test. But I'm going to cover what things change for the paired t-test compared to the independent t-test and the one sample t-test. So with the paired samples t-test, we're only going to look at the sample size of how many participants were in the entire study. So I like use N and then D, and D would be like for the differences, because there's a difference between, like if you look at the participants here, Jim is in the before and the after, and there's a difference between his score and the before and his score and the after. And the difference is really how many differences there are. So the difference between Jim's scores, the difference between Tracy's score, the difference between Corey's score, the difference between Chris's score, and the difference between Cole's score. So it's basically the sample size is just the number of participants, not the number of observations. It's the number of participants. So when we use the degrees of freedom for this specifically, it would not be like the independent t-test where we would have 5 participants in the first sample and we would, have a degrees of freedom of 4 plus 4 to have a degrees of freedom of 8. It is just there's 5 participants and we're going to subtract 1 for degrees of freedom of 4. So that's the difference that's going to change. So the one sample t-test was N minus 1 because you just have one sample. That's the number of participant or the number of observations minus 1. The independent t-test is adding the degrees of freedom from the first group to the degrees of freedom of the second group. And now with the paired samples t-test, it's the degrees of freedom for the number of differences that we will be utilizing or the number of participants, which is helpful for you. And I feel like it'll be easier once you see how this is calculated. So here is the test statistic for the paired t-test. So in the numerator is the mean difference. So we're going to talk about it's basically finding those differences. So x2 minus x1. So there's usually condition 1. You're going to subtract that from condition 2 and add the differences up and then get the mean of those differences. So there's what's called the mean difference, M of subtext D. And then your numerator in the numerator or in the numerator as well is mu of D. And mu of D is just based upon the null. If there is no significant difference between condition 1 and condition 2 or time 1 and time 2, if there's no difference, this is always going to be 0. So this is always 0. Mu of D is always 0. So it's the mean differences minus 0 divided by the estimated standard error of the differences. So basically, it's just your standard deviation of the differences divided by the square root of the sample size of the differences. So this is really the same equation ultimately as the one sample t-test. But we'll look and see how that looks when we're calculating it through. So it's still estimated standard error right here is the estimated standard error and it's SMD. And then our mean difference is in the numerator here. So here's how we calculate that mean difference. So we have some scores and we have before treatment and after treatment. Our before is always going to be like x of 1 and our after is x of 2. And I always present them in this order, the x of 1 and x of 2, because you'd always do like before and after. It's the only problem with that is it's counterintuitive to how we usually do math, because mathematically we always go left to right, but in reality, we want the first condition to be subtracted from the second condition. So think of it this way. If your score was 25 before and 22 after treatment, your score went down by 3 points. So this is a -3. So in actuality, you should be doing 22. Oops, sorry. Let me get this right. So sorry. 22 minus 25. sorry. And then for this one, it's 25 minus 30 because it went down by 5 points. 18 minus 18 is 0. 19 minus 21. So again, this is 19 minus 21. It went down by 2 points. 24 minus 27. It went down by 3 points. Now, once you have your differences, which is like D, and you can basically ignore the original data, and you're going to basically do a single sample t-test using just these right here. That's what you're doing. So if you add up your sum of the differences, the D differences, you should get negative 13. And because there's 5 differences, that's our sample size. So our mean differences is negative 2.60. It's just like you use sum of X, but instead it's sum of D because these are actually the differences. It is very important, though, that you're always subtracting the before treatment from the after treatment. If you were to go 25 minus 22, it would be suggesting this went up by 3 points. And then your mean difference would show a positive 2.60, suggesting that whatever you're treating, it increased by an average of 2.6 points, which is actually the opposite of what it did in reality. So we want to be careful that we're doing this in the correct order. So calculating the standard error is now the standard error of the differences. So that's why there's the SMD, because now you're just using those differences. So again, like I said, just ignore the original data and start working with just your differences. So now you have your sum of D, but now you're going to need a sum of D squared. So it's like a sum of X, but just D squared. So negative 3 squared should be 9. Be careful because if you square negative, it should be positive. So when you're putting that in your calculator, if you put that negative in there, just do negative 3 and you square it, it'll show a negative. That negative should not be there. You have to put parentheses in the right way. I just say if you're squaring a negative, drop that negative and just put the value in so you get the right number. So our sum of D squared is 47, because what we're doing is we're going to need to get our standard deviation. And to get our standard deviation, which is this, we need our sums of square of the differences. So sum of the differences, it's the sum of the differences squared minus the sum of the differences total squared divided by the sample size of the differences. So you could see that here, and you can see how it's plugged in. This sum of D squared is plugged in, right here. And then our sum of D is plugged in that numerator of that. And this is just 5, again, because there's only that one sample of differences. Calculate that sums of square divided by the degrees of freedom. Take the square root. Degrees of freedom is 4 right here. Standard deviation is 1.8166. So to get our estimated standard error, if you recall, and this should actually be a square root. I want to make sure that the calculation is correct. So I'm going to grab my calculator because I was not prepared. I want to make sure that it was calculated correct and we're just missing that square root accidentally there. 1.8166 divided by the square root of 5. Yep, the right number's there. I think in this it just lost that square root. There should be a square root around that 5. And we get 0.8124. This is probably where I see students make the biggest mistake. Again, this is the sample size, not degrees of freedom. The only time you use degrees of freedom is in your variance equation, which is right here. So remember, variance and standard deviation. The square root of the variance is standard deviation. So now you know how to calculate the standard error of the differences. So once you get all that, you plug it into your t-statistics. So let's look at what this looks like going through the 4 steps. So with this information, so we have testing the effects of a new medication to test whether there is a difference. And there's 4 participants, measured strength scores prior to the medication and then again after taking the medication for 1 month. It's a very common before and after type of test that is obvious paired samples T. And it says we're going to test at alpha 0.05. If we were to state our hypotheses, here's what we'd look like. Remember that null is H of O. There's not a difference in strength after taking the new medication. The alternative, there is a significant difference in strength after taking a new medication. So that's your prediction. So now we have research set up, our research scenario set up, and the hypotheses. That's step 1. Step 2 is setting that criteria. So here we have our scores for before medication, oops, sorry, after medication here. If you realize there's only 1, 2, 3, 4, because these are the same people in each of those. So we would do 4 minus 1 is our degrees of freedom, which is 3. If we look up in that T distribution table, remember we're using the T distribution table, we look up 0.05 because she said we're only looking for a difference. There isn't a direction. So that's a two-tell test. We're not looking for an increase or a decrease. We're just saying a difference. So our critical value is positive and negative 3.182. And I still say if you have difficulty telling whether something is significant based off of just comparing your test statistic to the critical value, draw it. So then you can see, okay, where does my test statistic fall? And then if it falls in these regions here, that's where we reject the null or we have found significance. Anywhere in here, there's no significant difference, okay? So now we've gone through step 2. Our critical value is positive and negative 3.182. So here's kind of how we would calculate this. So we have our before and after. Remember, you're going to subtract the before from the after. So this went down 5 points for person A. So it's down by 5. But this one went up by 21 points. This one went up by 23 points. This one went up by 25 points. So then we get our sum of D, which is 64. Then we get our sum of D squared, or sum. So you have to square each individual and then add, right? Which you end up with 1620. So then we get our mean as well. So that sum of D divided by the sample size, there's only 4 participants. We get a mean difference of 16. Now we have everything we need to calculate, because once we get our differences, we can ignore the original data, basically. No longer need it. You're just basically going to conduct that one sample t-test. So we're going to use the information that we calculated to get that sums of squares of the differences. So the 1620 is going to go right here. Our 64 goes in parentheses. That's the sum of D squared, just the sum of D, but you're going to need to square it. And then our sample size. So our sums of squared of the differences ends up being 596. So we can plug that into our standard deviation equation. That 596 divided by 3, take the square root. Now we have our standard deviation. Last step is to put this into our error equation, our estimated standard error of the differences, divide by the square root of 4. Our error is pretty large, 7.0475. Basically meaning that on average, the sample had an error of about 7.05 points. Like everything, there was an error of that amount. So when we plug everything in, so once we plug this into our equation, you see our mean difference. Oops, sorry, I'm trying to get my pen to work. Okay, there we are. Our mean difference was 16. Remember, we calculated that. 0, if you recall, is the mu of the differences. It has to be in that order. And then we plug in our estimated standard error here, 7.0475. And here is our test statistic, 2.27. And that is the value you compare to your critical value, is that 2.27. But we're still not done with step 3. We have more. So we need to calculate an effect size. Two most common effect sizes are Cohen's d and eta squared. Cohen's d is pretty much repetitive. The only thing that changes is now we're using the mean differences and we're using the standard deviation of the differences. So that's 16 minus 0 divided by 14.0949, and we get a Cohen's d of 1.14. So that just suggests that the sample mean shifted by 1.14 standard deviations due to the treatment, is what it did. With eta squared, again, these are our test statistic, the t obtained here and here. And when you calculate this, put this in parentheses. So you should get 0.63. So that basically means that 63% of the variability in strength, which was the dependent variable, was due to the treatment. Now, when you are calculating the on the exam and you're testing a hypothesis, you only need to calculate one of these, just one, and report one. You should know what both of these mean for the multiple choice questions, but you really only need to calculate one and report one. I always suggest calculating Cohen's d for any of the t-tests for one reason alone. It's going to increase the probability of you receiving more points, because I've seen a lot of students calculate their Cohen's d correctly, but got their t obtained wrong. But if you calculate your t obtained wrong, you're using the t obtained to calculate the eta squared. That means your eta squared is going to be wrong. So at least with Cohen's d, increases your probability of more points, if anything. So a little statistics for you. So then we still need to calculate the confidence interval. And the confidence interval for the paired t-test is now going to be your mean difference, that sample mean difference, plus or minus a t critical value. And again, remember, this is a two-tailed t, always, no matter what. Two-tailed critical value, always. Luckily, our test was already two-tailed, so we can use the one that we already had looked up, which was 3.182. We're going to multiply that by the estimated standard error. So this in reality is called the margin of error. I usually multiply those two together of error. I usually multiply those two together and then I subtract from the sample mean to get that lower boundary right here, and then add to the sample mean to get the upper boundary. So we have that lower and upper. So remember, the null is based off the null's mean difference, which is 0. If you look at a number line, and here is negative 6.43, and you look at the upper 38.43, our mean difference of 0, 0 falls somewhere over here, right? It's in between. So, right. So this basically is where we have found no significance if it's in between these 2 points here. No significance from here to here, because this is accepting that null is true. If it's out here, anywhere out here, it is significant. That null or the population mean, it is significant. So we will retain the null because it is within that range or those boundaries. So, and this would be a 95% confidence interval because we used an alpha 0.05. If you convert 0.05 to a percentage, that's 5%. 5% from 100%, that's 95%. So we can also, and I always suggest use your confidence intervals to determine whether it's significant, as well as comparing your t obtained to the T critical value. Our T obtained falls here, and it doesn't fall out in these areas, so we're not rejecting the null. This is no significance in the middle. So we are retaining the null. But again, we don't ever say retain the null in the APA statement. That's just theoretical. So we did not find significance. So here's how we could state this. There was not a significant difference in strength after taking a new medication, as T, and again, this is our degrees of freedom right here, is 2.27. Our p-value is greater than 0.05 because remember, p is greater than alpha when it's not significant. If it is significant, p is less than alpha when it is significant. So it's always going to be when it's not significant, p is greater than alpha. We used a two-tail test. We report n effect size. I choose to report Cohen's d. You just report 1. And your 95% confidence interval with the lower boundary, comma, the upper boundary. So you just went through everything with the paired samples t-test. If you have any questions or if you need to review other videos, I will have other videos for you available that goes through a hypothesis test with paired samples t-test. And please don't hesitate to reach out and ask more questions if you have any. Thank you.